You copy some super long link, fire it off to a friend, and it's a wall of gibberish nobody wants to click. Run it through a URL shortener, and it turns into 7 characters, clean and tidy. One tap, and you're there. This tiny little thing is actually a classic system design problem underneath. Today, we're going to design it from scratch. One machine can't handle it, so we'll add pieces step by step until it can take hundreds of millions of clicks a month. First, I want to use this problem to set a ground rule. The same system can be designed a bunch of different ways, and every one of them is a trade-off. I'm going to lay those trade-offs out for you. In this episode, I also want to break an instinct you might have. Not everything has to be handed to AI. This problem is exactly the counterexample. We'll save that for later. First, let's think it through. A URL shortener, at its core, does just 2 things. First, you give me a long URL. I hand you back a shortcode, and I record that pairing. Second, someone visits that shortcode. I look up the original URL, and I redirect them there. Basically, it's one giant phone book. The shortcode is the name. The long URL is the phone number. Writing is jotting down one line in the book. Reading is looking up a number by the name. Just those 2 moves. The hard part isn't the logic. The hard part is when this book has billions of rows and gets queried hundreds of times a second, how do you keep it fast and keep it from falling over? Let's build the most bare-bones version first and see when it buckles. 1 server, 1 database, 1 table, 2 columns. Shortcode, long URL. 1 comes in, insert a row. 1 gets looked up, search a row. It runs. It works. But you've got to work out the numbers first. Don't just wing it. This step is called back-of-the-envelope estimation in system design. It's real work, so let me walk you through it.
Going by the assumptions the primer gives us. 10 million users, 10 million writes a month, 100 million reads, a read-write ratio of 10 to 1. A month works out to about 2.5 million seconds. That's roughly 4 writes per second and about 40 reads per second. Store 3 years' worth, 360 million short links, and with the content that's about 450 GB.
See, 40 reads and 4 writes a second. One machine can actually still handle that. The real trouble is in 2 spots. One is how you hand out the shortcodes. The other is what happens when a hot link gets clicked like crazy. Those 2 are what make or break the design. Let's tackle the most central problem first. This 7-character shortcode, how do you actually generate it? There are several ways to do this. I'll lay out the 3 most common, and each has its sweet spot and its pitfall. First one, hashing. Take the user's IP plus a timestamp, glue them together, run 1MD5, get a string of evenly distributed random numbers, then base 62 encode it, and take the first 7 characters. This is the method the primer uses.
Base 62 just means encoding with 62 characters, 0 through 9, lowercase and uppercase. 7 characters can represent 62 to the 7th power, about 3.5 trillion, more than enough room for 360 million short links.
I actually ran this. Same IP plus the same timestamp, computed twice, gives the exact same shortcode. Both times it's this, 5M3JHC7, which means it's reproducible. But that's also where the problem is. Hashes collide. I deliberately shrank the shortcode to 4 characters to blow up the odds, and across 200,000 entries, it collided over 9,400 times. In production, you use 7 characters, so the odds of a collision are tiny, but not 0. So the hashing approach needs a backup move. The shortcode is a unique key in the database, so if you hit a collision on insert, you just generate a new one and insert again. Second method, an ID generator. No hashing. You use an auto-increment ID, 1, 2, 3, 4, climbing up, and each ID gets base 62 encoded into a shortcode. Here, look, I actually ran it. ID is 1, the shortcode is 1. ID is 62, the shortcode is 10. ID is a billion, the shortcode is just 6 characters. It never collides by design. And you can even decode it back to the original number, microsecond level, blazing fast.
But it has two pitfalls. 1, the shortcodes are monotonically increasing, so someone can guess the next one and crawl your whole site. 2, where does this auto-incrementing number even come from? On a single machine, it's easy, but the moment you go multi-machine, this ID generator itself becomes the narrow bridge every write request crowds onto, a hotspot.
Third one, you set up a dedicated key generation service that pre-generates a big batch of random shortcodes up front, stores them, and hands one out whenever someone needs it. Used one, crossed off. No collisions, hard to guess. The cost is you're running one more service, and you have to manage the pre-generation and deduplication. See, there's no free lunch. Hashing is simple, but you have to handle collisions. The ID generator is fast but guessable, and it has a hotspot. The key generation service is clean but adds a layer. Which one you pick depends on which one scares you more. Shortcode, sorted. Next up is the API. Just 2 of them. On the right side, you post a long URL. I return a shortcode. On the read side, you jet the shortcode. I redirect you away. I actually wrote this minimal service and ran it. PAW-st, one of the primer's links, and it hands me back shortcode 1. Then I GE/1. Look at this real response header. HTTP 302 found, with location pointing back to the original URL. The browser gets this and automatically jumps over. There's one detail really worth talking about here. Whether to redirect with 301 or 302 is a genuine trade-off.
301 is a permanent redirect. The browser and CDN cache it, so the next time someone clicks that short link, it never even reaches your server. The upside is it saves you a huge number of requests. The downside is you lose the click data. 302 is a temporary redirect. Every single click comes back to your server, so you can track who clicked and where they came from.
So why do URL shortener companies almost all use 302, willingly taking on all that traffic themselves? Because click analytics is the lifeblood of a URL shortener. It's where the money is. What they want is for every single click to pass through their hands. So this isn't about which one is technically better. The business decides the technology. Last piece, how the reads hold up. Don't forget the read-write ratio is 10-1, and the traffic is extremely uneven. A handful of viral links eat up most of the clicks, a classic 80-20 distribution. So you shouldn't hit the database on every single read. You put a cache layer out front and keep the hot short links in memory, Redis, for example. The vast majority of reads hit the cache and return right away, never even touching the database. Further out front, you can add a CDN too. Now let's put these pieces together and watch it grow from one machine into a system that can take the load. This is the most satisfying part of system design. Architecture is grown, not drawn up perfectly from the start. Step 1. Single machine, one app plus one database. Too many reads and the database buckles first. So step 2. Add a cache out front, hot links go through memory. The app box gets overwhelmed too. So step 3. Add load balancing with several app servers behind it. Data piles up to billions of rows, and one database can't hold it. So step 4. Sharding, consistent hashing by shortcode, spreading the data across multiple machines. And the number issuing for write requests shouldn't crowd onto one box either. Break it out into its own key generation service. Don't forget to talk about failure. What happens if the cache goes down? All the reads slam into the database, and it can cascade into a collapse, so the cache needs graceful degradation and warm-up. One database shard goes down. That slice of short links can't redirect, so you need replicas and primary replica failover. Design isn't about drawing the path where everything goes smoothly. It's about drawing the path for when things break. All right, time for the recurring segment every episode has. How would AI change this? And this episode, I'm going to give you an answer that might be counterintuitive. In the core path of a URL shortener, AI has almost no place. Think about what we just designed. Issue a code, look up a table, return a 302. This is a deterministic problem. Base 62 plus an auto-increment ID solves it in microseconds, stable, predictable, and practically free. If you force a large model in there to generate shortcodes, you're taking a microsecond problem and piling on hundreds of milliseconds of latency, a token bill, and the occasional flakiness of non-determinism. That's not an upgrade. That's making trouble for yourself.
So where is AI actually useful in this system? At the edges, not the core. For example, judging whether a target link is phishing or malicious, that's a classification problem, and models are good at it. Or detecting sensitive words and abuse in custom aliases. These are reinforcing the guardrails, not building the engine.
So what I really want to give you this episode isn't a URL shortener, it's a sense of judgment. In the AI era, one of the most valuable skills an engineer has is being able to recognize it. This is a deterministic problem. AI shouldn't show up here. This keeps replaying throughout history. If a regular expression can solve it, don't reach for machine learning. If a config file is enough, don't stand up a whole database. Once you've got a new hammer, everything looks like a nail, and that's the most expensive mistake there is. The ones hit hardest by this wave of AI impulse are, honestly, us engineers ourselves. So I'm treating this episode as one honest reminder. Knowing how to use AI is a skill. Knowing when not to use AI is the rarer skill. Before we wrap, a few real pitfalls. Don't skip them. 1. Shortcodes are guessable. With an auto-increment ID, someone can follow the numbers and crawl every link on your site. And when privacy's involved, that's dangerous. Either add randomness or use a key generation service to scramble it. 2. Expiration and deletion. Short links can't be stored forever. You need an expiration policy, and someone has to absorb the cost of cleaning up expired ones.
3. Hotspot skew. An 80-20 distribution means a tiny few viral links can overwhelm a single cache node or a single shard, so you have to handle hotkeys separately. Never assume traffic is uniform. The primer's very first assumption is uneven traffic. Don't forget it.
4. When not to build it yourself. If it's just for internal use at small scale, an off-the-shelf shortener or a single database table is plenty. Don't jump straight to sharding and a key generation service. That's over-engineering. The design has to match the scale of the problem. My takeaway is one sentence. A URL shortener is a great problem because it's small enough to see through at a glance, yet complete enough to bring in every trade-off: estimation, code generation, caching, sharding, redirects, all of it. And the biggest thing I took from it, funny enough, is that boundary line for AI. First figure out whether it's a deterministic problem, then decide whether AI gets to play. If you want to get hands-on next, take my minimal service, add a Redis cache layer yourself, load test the hit rate, and you'll instantly feel what that 10-to-1 read-write ratio really means. The code and the steps to reproduce are down in the description. The same system can be designed many ways. Next episode, we'll pull apart another one. See you next time.